Alright, so we did adding by diagram, so we should probably do adding by coordinates. So let's talk just a little bit more about vector addition. Okay, so if I want to add a vector 1, 2 to a vector 3, 4, I know it's super creative, right?
4, 6.
Why?
Just do 1 plus 3.
Why?
The x's add to the x's and the y's add to the y's.
Why?
That's what they told us.
Okay. So somebody at some point told you that you can just add the x's together and add the y's together, right?
Why? Because
No. Because that's how pushing works. Right? So, what do I mean by this? I mean, okay, I'm going to take the vector, right, the arrow that ends where for this first one? At 1, 2. So I'm going to go over 1, up 2. Here's a dot. I need an arrow that ends there, right? That's this first one. Then, where's this guy? Over 3, up 4. So that's like here. I got an arrow that looks like this. And then how do I add these together?
Stick one on the end of the other.
Yeah, stick one on the end of the other, right? Okay, so if I stick the idea of over 3 up 4 onto the end of the idea of over 1 up 2, what are you going to end up doing? Yeah, you're over, right? You're getting 1 over from the black arrow and 3 more from the blue. That's going to make a total of over 4, right? And you're going to get a total of, let's see, so I'm over 4, I'm someplace in here, and then I'm going to get an up 2 from the black and an up 4 from the blue. It's going to give me a total of 6, up 6. Right? And that's exactly what would happen if I added the blue arrow to the end of the black arrow, or the black arrow to the end of the blue. You guys see that? So it's not magic that you add coordinate-wise, it's just because that's kind of how you think about a vector. And really, actually, that's kind of me looking at this thing and thinking that this is 1, 0 plus 0, 2 already. You guys see that?
into its components.
Yeah, that's me thinking about that black arrow as this vector here and that vector there added together. You see that littler picture? So of course, if that's the way they, like, if tip to tail's the way they work, I can think about this one as those two. And that means I can think about the blue one in a similar way, and then I can just count all the overs and all the ups. In 3 dimensions, is that going to be any different at all? Nah, just way, way harder to draw. Right? But otherwise, it's the exact same thing. Let's see, what else can we ask? Oh, we should probably ask about 0. I don't know, you guys can develop a theory here. What about 0? What's special about 0 in Numberland?
It's a placeholder.
It's a placeholder.
It has so many rules that like
Yeah, what's this? So we're doing addition, right? So what's 0's rule with addition and then in like regular one-dimensional Numberland?
Doesn't change anything.
Yeah, it doesn't change anything, right? So is there an arrow that you could stick on the end of a, like, say I had this arrow here. Is there an arrow I could stick on the end of this that would leave it unchanged?
a 0 vector.
Yeah, it seems like a 0 arrow, right? Like maybe that one? Right, the arrow that's not any long? That seems like it would leave it unchanged. So the 0 vector, right, is this guy in 2 dimensions. And that has the exact same property. When I add it to something, I get that something back. So usually we denote this thing as 0 with a little vector hat on it.
Now it's 0 vector.
Yep. And that thing has the property that if I take a vector u like this one and add the 0 vector to it, I get
Vector
u back.
Yeah.
This,
Yeah, and
this is
some
all
of
we
you
did
have
for
linear
full.
algebra, which is really weird.
Yeah, we were supposed to take this class before.
It's just how it
Should've.
ran.
Yeah, it happens. And it works okay. It just
Don't worry, a few of us
It
dropped
won't
it.
transfer though.
You were
Okay.
there for this
I'll
part.
take it in the spring.
any questions on this? You guys okay with component-wise addition? Okay, cool. Yeah, we're gonna do Euclidean inner product.